Hi, my name is Paramita and I am one of the tutors for this course. Today I am going to give you some hints for solving assignment number 3. Let us start with problem number 1, which is problem number 2.41 from Griffith's book. So we start with problem number 1, which is 2.41. Alright, so it is given that there are two metal plates and charge on this metal plate is Q and they are having area A and the separation between these two plates is D. Now it is asked that we need to find out the electrostatic pressure on the plate using two methods. One is from the force expression and B is by using energy. So first you will be doing this problem, you will be solving this problem by using sigma, and you already know that the electric field from this plate is like this because it is given a plus Q charge. Similarly for this plate it is like this going outward. Now you can see that inside this region between these two plates E inside is 0 and E outside is non-zero. So now you have to find out E out, and you already know that E between the two plates is 0. So you know that pressure is half epsilon naught E square. By knowing E out and E in, you can now find out the pressure on the plates. Now we will solve this problem using the energy. Let us try to visualize the thing, like how will we calculate the energy, the electrostatic energy between in the plates. So now let us see that, let me redraw this. Alright, so these are the plates with having area A. So the separation is now D and the charge is Q. Now let me move one of the plates by a distance, say delta x. So now the separation between the two plates is, so this is a new position of the plate. So now the separation is actually not D but D plus delta x. You can also see that the region between the two plates is now increased. It is now having a volume A times D plus delta x, which was previously A times delta x. So the volume in which E equal to 0 is now increased by amount A times D plus delta x minus A times delta x, which is A times this should be A times D. This should be A times D because D was the old volume. So now the new volume is D plus delta x times A. So the change in volume is actually A times delta x. Now the electric field between the two plates is always 0. So if you increase the volume, then the volume in which E inside is 0 is getting larger. So the energy actually drops down. So you will see that delta E goes down as the separation between the plates, that is the volume in which E in equal to 0 increases. You get the point. Now you see delta E decreases. So now from the knowledge of energy density, which is half epsilon naught E square, if epsilon naught is the permittivity. So energy density, from the knowledge of energy density we can find out delta E. You have to find it out. Now you know that pressure, the electrostatic pressure is dE dx, or I can write it like, sorry, dE dV, delta E delta V. So I know what is my delta V, I know what is my delta E, so I can find out the pressure using energy. Here energy I should write W, because E already we have used for electric field. So let me write it as W, not E. So all right, that solves the first problem. Now let us move on to the second problem, problem number 2, which is a similar problem, but this time you will be encountering a metal sphere. So you have a metal sphere having radius r, and z axis is like this. Now it makes an angle theta. All right. So you are asked to find out the force between the two hemispheres, the northern hemisphere and this is the southern hemisphere. You are asked to find out the force between two hemispheres. All right. So how will you do it? Like we did in problem number 1. Okay, problem number 2 is 2.42 in Griffith's book. Okay, so how will I do it? So first thing is to find out E average, that is the average electric field. So as you have learned from your lecture notes that E inside of a metal sphere is 0. Now we are going to find out the E outside, the electric field outside the metal sphere using Gauss's law. So Gauss's law says that E dot dA, closed surface integral, is Q enclosed by epsilon naught, if epsilon naught is the permittivity of the space. All right. So now let us recall how we find out the electric field outside a metal sphere. Say I want to find out the electric field at a distance r from the center, C be the center, this is the z axis making an angle theta. Okay. So now I can take a sphere and then I write E is Q enclosed by 4 pi epsilon naught r square, this is my E out, and if I take the vector it will be along radius r. Now from the knowledge of E in and E out, you can find out what is your E average. So from the knowledge of E average, now you can find out the force per unit area. Let us call this force per unit area as small f, and that is equal to sigma times E average. To find out the force between the two hemispheres, you have to find out the z component of the two force. So, you already know what is the angle between the z axis and the radius. So, now you can find out that E average z component will have a dot product between r and z cap. So, using that you can find out your force per unit area, which I call as small f, and the z component of this will be sigma E average z component, and that will give you the E value, and then you get a dot product between z and r. So, this is the force per unit area. To find out the total force, you have to now integrate this small f over the surface area. So, when you do that, you get the force between the two hemispheres. So, that solves the second problem. Now, there is one more part to the second problem. We expect you to calculate the force using energy. And how will you do that? Remember, in the first problem what we did was, there were two metal plates and there was a fixed distance between the two metal plates. That distance was d. Then what I did was, I shifted the first plate to a very small distance, say delta x. So, now the separation becomes not d but d plus delta x. So, you can see that E inside equal to 0 increased. So, the volume actually increased, in which the E is 0. Similarly, I will do the same thing in case of metal sphere. So, it was a metal sphere with the northern and southern hemisphere. So, what I will do is, I will now shift this sphere to a small distance, say delta x. So, what will happen is, now you can see this was the volume, now the volume is increased, you can see that. I just pulled it up, so I get this volume extra, right. So, the volume in which E inside is 0, because you know from the lecture note that inside the metal sphere you have the E, the electric field to be 0. So, E inside is still 0 here, but the volume increased. So, what will happen is, energy goes down. So, what I will have is delta V, this V is volume, its delta V is increased because I pulled one of the hemispheres, say northern hemisphere. So, delta W will decrease. Okay. So, now you know what is your energy density, right. Energy density is already known to you. So, from the knowledge of energy density and from the knowledge of increase in volume, you can find out the pressure, I am sorry, you can find out the force because force is energy per unit change in energy per unit change in length or distance, whatever. So, you get dW dx. Now, you know what is your change in energy, dW is known, you have found out, and then you find out the force. This is the second problem. Let us now move on to the third problem, which is problem number 2.50 from Griffith's book. So, this is problem number 3 in our assignment number 3. All right. So, potential is given as A e to the power minus lambda r by r, where A and lambda are constants. So, you need to find out in A, you have to find out what is your electric field corresponding to this potential. B is to find out the charge density, and C is to find out the total charge. How will I do it? For part A, you know that electric field is minus of grad V. Now, look at the potential. It has two functions. One is Fr and another is Gr, where Fr is e to the power minus lambda r, lambda being a constant, and Gr is 1 over r. So, when you calculate E in part A, you have to find out the gradient of this potential Vr, where you will encounter these two functions. Now, how to calculate this? Now, you know that gradient of two functions is like g grad f plus f grad g. We have defined what is our g and what is our f. So, we can immediately find out this quantity. So, that gives you the electric field. Now, the part B is pretty straightforward. It is rho r, which is epsilon naught divergence of E, and E is already known to us. So, this is basically minus epsilon naught del square V r. Now, del square f g we need to find out. So, remember that del square f g is del square f g plus f del square g plus 2 grad f dotted with gradient of g. So, now from here we can find out the charge density. Here you will encounter divergence of r by r square is basically 4 pi delta r. Alright. So, now in part C, we have to find out the total charge, which is nothing but rho d cube r. You have already found out the rho from B. Now, use that rho to find out the total charge. Here you may encounter delta function integral, and you know the result. This is 1. So, use it and find out the total charge. So, this solves question number 3. Now, I will solve question number 4 from your assignment number 3, which is question number 2.53 in Griffith's book. So, 2.53, it deals with a non-linear device, which is vacuum diode. In this case, the potential and the current is not linear. So, that means if I plot potential as a function of current, I will not get a linear plot, but the plot will be a non-linear thing, because here Ohm's law is not obeyed. Okay, let us just quickly review Ohm's law and what we have learned in this. If I have a source, say a cell, so I have here a rheostat whose resistance can be varied, and now in series I put a ammeter. With this I join a resistance, known resistance, say R. So, if I now put a voltmeter, across this known resistance, I will find that if this is RH, a variable resistor. So, what I will see is I can regulate the current in the circuit and I can find out the voltage. Now, if I plot the voltage as a function of current, I change current and I simultaneously I get the voltages. So, what I will do is I plot the voltage as a function of current and I will get a linear graph, and the slope of the graph will actually give me the resistance. So, V is proportional to I. But in case of a vacuum diode, what happens is space charge is built up very quickly in between these two plates. This is cathode and this is anode. This is kept at a positive potential, say V naught, and this is kept at a potential, say V equal to 0. So, the separation between two is D. So, electron comes out of this cathode and moves towards the anode because it is kept at a positive potential. So, we get a cloud of space charge over here. Okay. This is space charge. Now, in the first part of the problem, what is it says that you have to write the Poisson's equation. You know what is Poisson's equation in 3 dimension. This is del square V is the source divided by this charge density divided by the epsilon naught, where epsilon naught is the permittivity, right. So, here we are dealing with 1 dimension. You can see if I say this direction is x, so I am dealing with 1 dimension. So, I can write the Poisson's equation in 1D. So, that solves the first part of the problem. Let us now move on to the second part of the problem. In second part, what we have to do is we have to find out the velocity of electron at any point, say x. So, I call the velocity to be ux. So, I want to find out the velocity at any point, say x, d being the total separation between these two plates. And ux can be found out using the kinetic energy and the potential energy. You know the kinetic energy would be half m u square and potential energy is q times v. So, now knowing the kinetic energy and the potential energy, you can find out the velocity. Now, you know that the potential energy is qv, v being the voltage. Sorry. So, you know that half mv square equal to qv. So, half mu square, u being the velocity. So, u is 2 qv by m square root. So, this is the velocity of the electron at any position, say x. Now, we move on to the third part of the problem, which says that in steady state, what happens is I is independent of x. Then you have to find out the relation between rho and v. You know the constants and you know how I is related to the charge. I is the rate of change of charge flow. So, this is basically ddt of rho times dv because Q is rho times the volume. So, now from there you can find out what is the steady state current. Now, in number D, you start with A and then using your results from part B and C, you derive the second order differential equation in V, and you find out that it is proportional to V to the power n, where n is not equal to 1. You need to find out your n value using A, B and C. In part E, you are asked to find out the solution for V as a function of x V naught, V naught is the potential at the anode, and the separation distance d, and then you have to plot Vx, and then you have to compare it with the case where we are not dealing with the space charge. And how will you do it? To solve this equation, whatever you obtained in D, where n you have to find out what is this number n, you have something like this, right. So, if it is proportional to V to the power n, then you know that it should be equal to some constant times V to the power n. Now, how to solve a differential equation which involves the second order derivative? The trick to solve this kind of equation is you multiply 2 dV dx both sides. Now, when you solve this equation by multiplying 2 dV dx both sides, you get 2 dV dx d2 V dx2 will be equal to, I am multiplying 2 dV dx both sides, constant 2 dV dx at whatever is here V to the power n. So, when you solve, you already know what is this n. I am not writing it because it is your assignment. So, now what I will do is, you can immediately see that the left hand side is d dx of dV dx square, and the right hand side is 2 times the constant that you found out here, and then V to the power n dV dx. So, when you integrate this, you get dV dx square is equal to 2 times the constant and then Vn dV. Plus some constant, say C. Okay. So, you basically get dV dx square is 2 times constant times V to the power n plus 1 by n plus 1 and then the constant C. Now, how to find out this constant? For that, you have to use the initial condition, which is at x equal to 0, V0 is 0, and at x equal to d, Vd is V naught, that is the voltage at the anode, and this is the voltage at the cathode. Okay. So, now using that you can find out the value of C. So, C is now known. Now, you have to solve this problem, this equation. So, then you get V as a function of x. So, V will be some other constant, say constant prime, and then you get this x to the power something, say some gamma plus d. Then you again have to use the initial condition and then you find out V finally. So, this is Vx as a function of x. Now in part D, you are asked to plot Vx as a function of x. So whatever you get here, this dependence, you have to plot it. In part E, it is said that without the space charge, Vx changes linearly with x, which is quite evident. You can see that if there is no space charge, then Vx will be actually V0 d V0 x by d. You can immediately check that at x equal to 0, this quantity is 0, so you actually reach V0 equal to 0, which is fine, and at x equal to d, you have Vd, which is V0. So this is fine. So now you have Vx is V0 x by d without the space charge. Now you can plot that how Vx will look like. It is actually a linear function. Now in F, you have to find out the expression for current. By solving the differential equation d2v dx2 equal to some constant v to the power n, you can actually find out this constant in terms. So from there you can find out I. So this is the fourth problem, and now you can see the difference between the linear and nonlinear system. When you plot it, the v with respect to I in the first diagram we have seen, this is the verification of Ohm's law, and you expect something like this, a linear function. Here what will happen is V is not proportional to I, but I can write I is V0 to the power some other number, say some gamma, where gamma is more than 1. Here you see that V, if I write I, is actually proportional to V to the power some gamma. So gamma is obviously not equal to 1. If it was 1, then we could have Ohm's law obeyed, but you can see that Ohm's law is not obeyed in non-linear devices like the vacuum diode. It's a very good example of a non-linear device. So here you get a non-linear dependence between I and V0 to the power gamma. So gamma you have to find out. Once you get gamma, you can see that we get a non-linear relationship between the space charge induced current and the voltage. That solves the fourth problem. Thank you.
Hello friends, I will be discussing problem number 5, 6 and 7. So let's start with problem number 5, which is how to do it. Okay, problem number 5, which is 3.1 from Griffith. So this is similar to the problem in section 3.1.4, except here that you are having a charge which is placed in inside the sphere, and you have to find the average potential due to the charge on the surface of the sphere. Okay, you need to find average potential due to the charge Q. So the potential due to the charge Q at this point exactly is V, which is K, Q divided by obviously R prime minus R, where K I will just write as this. Okay. Now if you want to find the average over the spherical surface, it will be just K Q divided by 4 pi R square integral over dA, this particular area dA here, divided by R prime minus R. Okay. This is a very important point to note. This particular thing here, because this is nothing but the potential at R prime due to a unit surface charge at R. Okay, and this will be exactly 4 pi R square divided by 4 pi R into sigma, which is obviously we have. Okay, so let's rub this since we cannot see. I will just write. Okay, due to unit surface charge density at R. Okay, and this is equivalent to 4 pi R square sigma divided by 4 pi R. So obviously here we'll take sigma equal 1 since we have set unit surface charge density. So in this way you can proceed with the rest of the problem. Now let's go to the next problem, which is problem number 6. Which is 3.4 from Griffith. So here what we have is again a sphere, and I have a charge Q outside the sphere, let's say, which is at a position vector R prime. So what you need to find is the average of the electric field over the spherical surface. And you need to also show that this is exactly the electric field due to the charge Q at the center of the sphere. Okay, if I would put here center. Now, so I know that at this point the electric field due to the charge Q will be again KQ divided by, let's say I don't have this, R prime minus R divide by R prime minus R, okay, Q. Alright, now the E average, okay, will be just KQ divided by 4 pi R square into R prime minus R divided by R minus, okay, Q dA. I would consider again this particular area element dA right here. So in the same argument that we proceed in the previous problem, we said that this particular term is like a potential at R prime due to a unit charge density at R. So here also I would say this term is nothing but the field at, let's say, R prime due to unit surface charge density on the R. Okay. So the rest I will leave to you for this particular problem. Now let's go to problem number 6, which is 3.37 from Griffith. Now, so here you have the same kind of geometry. You have a charge Q at a position vector R prime, and let's discuss about this problem properly. See, in section 3.1.4 we said that the average potential over the spherical surface is equal to the net potential at the center of the sphere. Let's call this okay. Now that means if you take a sphere of any radius, the average potential due to the charge Q will always be the same. You take a sphere of any radius, that means d V average over dr is equal to 0. This is one way of interpreting the statement. Now here what we are going to do is, here you have to give the same argument, okay, by just relying on the Laplace equation. Okay. Now let's see. Now V average, let's write again like this over the spherical surface, let's say, which is of radius r, is nothing but a closed integral V dA. Okay. So if I consider a spherical element at this point, I can write this like 4 pi r square V r square sine theta d theta d phi. Now since the integral is over theta and phi, I can cancel out r. Then if you take the derivative with respect to r, you will get 1 by 4 pi dv dr sine theta d theta d phi. Okay. Which this equation I can write exactly like this. Then okay. A gradient of V dot r cap and r square sine theta d theta d phi. So or dr, which is equal to 1 by 4 pi r square del gradient V dot r cap dA. Now, just like we have discussed, we have to show that the derivative of the average potential with respect to R is 0. So you can show from this equation by using divergent theorems. So which I will leave it up to you. Okay, thank you.
Hello, my name is Vinay. So I'll be discussing solutions hints for the solutions for the problems 8, 9 and 10. So the problem 8 is about buckyballs, which is carbon 60. So it has a C60 ion which is negatively charged, and that can be approximated as a conducting spherical shell with a charge E minus, where E minus is the charge of the electron. So you have a spherical shell, and then there is a charge E minus, and so by problem 3.9 you already know that a conducting spherical shell at a constant potential can be replaced by two charges. One is Q double prime at the center, and then there is a Q prime which is placed at some distance b, and the total distance is a. Okay. So from problem 3.0 you already know that B has to be at a distance r square by a, where r is the radius of this spherical shell, and then there is the charge q prime has to be minus q r by a. So in this case it is the charge of the electron, so it will be equal. So the force will be given by q prime E minus by a square plus q double prime q prime E minus by a minus b whole square and then q prime E minus by a square and 1 by 4 pi epsilon naught. Okay. So in this case, in problem 3.9, you had put q prime plus q double prime to be 0 because the conducting spherical shell was neutral. But in this case, the total charge has to be E minus. So keeping this in mind, one can find the distance a for which the electron which is placed near the conducting spherical shell is at equilibrium. So f is equal to 0, and you solve the equation and get the required a, which is the a naught, which I am calling as a naught. So this is problem A of 3.41. Then problem B goes as follows. In this case, you just have to find the work done. So from the position at which the force is 0. So you have some a naught which you have determined from the previous problem A, and you just find out the integral. So this is the hint for the problem B. Okay. Okay. So the next problem is 3.51, which is problem number 9. So in this problem, you have to use the Green's reciprocity theorem to find out the induced charge on the plates of the capacitor when a charge q is placed at distance x from one of the plates. So this potential is 0, this potential is 0, and the total distance between them is d. And okay, so for in order to apply Green's reciprocity theorem, you need two situations. For situation 1, you will use the actual situation. So VL1 is 0, where L1 is the potential on the left plate. VR1 is also 0, and QR1 is equal to Q. And in the situation 2, what you do is you have one of the plates at some potential V0 and the other plate at potential 0 with no charge in between. So VL1 is 0, VR1 is V0, and QR2 is 0. Sorry, this has to be QX, QX1. Okay, so then what you do is apply the reciprocity theorem. So V1 rho t d tau is equal to V2 rho 1 d tau. So in this case, it will be VL1 Q L2 plus VR1 QR2 plus Vx1 Qx2 is equal to VR1 VR2 VL2 QL1 plus VR2 QR1 plus Vx2 Qx1. So once you apply this, you will find the charges on both the plates, on one plate, and then you do the opposite of this. So you have now you have left one at V0 and right one at 0, and then you apply the reciprocity theorem, and that will give you the charge on the other plate. So this is the hint for problem 3.51 A, and in B you will have to basically use the same procedure, but this time it's concentric spherical shells. So you have both of them grounded, and then there is a charge Q at some distance, and you are supposed to find the induced charges on both the surfaces of the spherical shell. So for instance, this is at some A and this is at some B. So this distance is B. Okay. So this is your situation. This is the actual situation given. So what you do is, this is the actual, and in the, so the situation that you choose will be one where in one case the inner one is still grounded, but the outer one is at some potential V is equal to V0, and then you apply the reciprocity theorem. So in this case it will be VA1 QA2 plus VB1 QB2, then VR1 QR2 is equal to VA2 QA1 VB2 QB1 plus VR2 QR1. So this will tell you the induced charges, where VA1 is the potential on the surface of the spherical shell with the radius A, and VB1 is the potential on the surface of the spherical shell with radius B. And you do it in this situation, you will find the induced charge on one of the surface, and then in the next situation what you do, you consider the inner spherical shell to be at some potential V0 and the outer spherical shell to be at some to be grounded, and then you apply the reciprocity theorem, you will find the induced charge on the other surface. Okay. So this is the hint to the problem B. So the 10th problem is very simple. So there you are asked to find the work done assuming on charging a capacitor to a potential V, assuming the charge to be quantized. So you know that the potential is the work done per unit charge. So you integrate over the charge in the continuous case, but because the charge is considered to be quantized in this case, you have summation over Vi Qi, I from 0 to whatever is the number of electrons, that total number of electrons that you are choosing. So it will be n minus 1. Okay. So but note that in this case the potential will depend on the number of electrons that have been transferred. So in each case it will be different. Okay. So if you do this, you will find the total work done.